6.1 Random Variables. Let's say we toss a fair coin 3 times. The sample space for this process is all of these results. Remember, a sample space is everything that can happen, so we can get anything from all 3 heads to all 3 tails, or any combination of that in between. There's 8 equally likely outcomes, and the probability of any of these particular events occurring are all 1/8. Now, we may not be interested in the probability of getting exactly heads, tails, which would be this one right here. And instead, we might be looking at what's the probability of getting exactly 1 head and 2 tails out of 3 coin tosses, regardless of the order that they come in. Let's look a little closer at the random variable x, which is the number of heads that we get in 3 tosses of this coin. And x can vary, but it's always going to be one of the numbers from 0 heads to 3 heads. So to get 0 heads, a very precise set of events has to happen, namely that we get tails every time. But there's a few different ways that we can get exactly 1 head or 2 heads out of 3. There's not just one way that those events can happen. So when it comes to organizing the information for the number of heads that we get out of 3 coin flips, we might want to make what's called a probability distribution. So a probability distribution will show us all the results that a variable can take. We're talking about the variable number of heads that we get, and it can result in anything from 0 to 3. And we also have underneath that their associated probabilities. 1 out of the 8 options had 0 heads, 3 out of the 8 had 1 head, etc. Now, there are 2 types of probability distributions which correspond to the 2 types of random variables. We have discrete data and we have continuous data. When we're talking about the number of heads that we get in 3 coin flips, this is a discrete random variable because this is countable. Okay? In 3 tosses of a coin, we might get 1 head or 3 heads, but we'll never get 1.2 or 1.84 heads out of 3. So a discrete variable is a countable variable, and it has a fixed set of numerical values that have gaps in between them. We'll get 1 head or 2, but not in between. One of the benefits to having a probability distribution set up is that we can answer a lot of the probability problems that are associated with this. For example, let's say we're asked, what's the probability that we get at most 2 heads? Well, at most 2 will include anything from 0 through 2. So we would just add up those associated probabilities and get 7/8. Similarly, we could use the complement rule, which is subtracting the events that are outside what we're looking for. So rather than dealing with the 3 events that are part of at most 2, we could find the 1 situation that's not included in that and subtract it from 1 to get what we're looking for. In this next example, we're looking at Apgar scores, which are scores given to newborn babies assessing their health from 0 to 10, and they rely on variables such as breathing, skin color, heart rate, etc. Here we have a probability distribution with the random variable Apgar score. That's our x. Values range from 0 through 10. We have their associated probabilities down here, and note that one of these is missing. All right, so to start, we're going to write the event. The baby has an Apgar score of 3 in probability notation and find its probability. So to write this statement right here, the baby having an Apgar score of 3, in probability notation, we can just write it as P of x equals 3. Since that's the only value that's missing from our table here, we can figure out what it is by using the complement rule. All of the other things added together, which are all of these other boxes, okay, it leaves a leftover value of whatever that cell equals. So in this case, we get 0.008. In part B, Apgar scores of 7 or higher indicate a healthy baby. What's the probability that a randomly selected newborn baby is healthy? Well, it's just going to be these probabilities added up. And we get 0.908. Those examples were for discrete random variables. Contrast that with a continuous random variable. So when we have a continuous variable, it can take on any value in a number line, like 0.84522 or 9.1111119, or here we see the digits of pi. So when we look at a problem to determine if it's discrete or continuous, discrete variables are typically counted. We have valid values with gaps in between them, like the number of heads we get when we flip a coin 3 times. Can be 0, 1, 2, or 3, but it can't be anything in between those numbers. On the other hand, continuous random variables typically result from measuring something, such as the weight of an adult male elephant, or the height of a tree, or the volume of water in a cup. So let's classify each of these values as either discrete or continuous. Part A, x equals the foot length of a randomly selected student at your school. This would be continuous because it's measured. It might be 9 inches or 10 inches, but it could also be any value in between that. Part B, G equals the number of pumps out of 12 in use at a gas station at a randomly selected time of day. This one's discrete because maybe there's 2 pumps in use or 3 pumps, but it's not possible that there would be 2.349751 pumps in use. Lastly, part C, T equals the string tension of a randomly selected tennis racket. Again, this is measured, making it continuous, and that tension could be any value within a range. The way we solve problems involving a continuous random variable is with a density curve. Now, we've used density curves before. The most common one is the standard normal curve that we've seen and used with that Z table. However, not all distributions are normal, and sometimes we have to make our own density curves. So let's say we have the random variable x. It's going to be a randomly generated number between 0 and 10, and it's not just integers, so it can be 7.3549. We want to find the probability that we end up choosing a number between 3 and 7. So let's draw this out. So we have what's called a uniform density curve, meaning all of these probabilities are equally likely because it's just going to give us a random number between 0 and 10, and none are more likely than the others. Now the base of this rectangle here that we're going to draw is 10. And we're going to choose a height for our rectangle to create a shape with an area of 1, because all density curves have an area of 1. So our height is going to be 1/10, because we know the area of a rectangle is the base times the height, and that would give us an area of 1. Uniform density curves are really easy because it's just a simple calculation. We want to find the area under this density curve between 3 and 7. We have that shaded in our diagram there, and we're just going to do base times height because this is a rectangle and we're finding the area of that rectangle. So the base is 4, the height is 1/10, and again that was chosen specifically because 1/10 times 10 equals 1, which is the whole area of that rectangle. Okay, again, any density curve will have an area of 1. And when we do this calculation up here, we get a probability of 0.4 that we would get a number between 3 and 7. As mentioned, this is the most common kind of density curve that we use in this class. This is the normal curve. We went over this way back in chapter 1. However, as a refresher, 68, 95, 99.7 are the numbers in the empirical rule. That's giving us the percent of data within 1 standard deviation for the mean, 2 standard deviations of the mean, and 3 standard deviations of the mean. So for an example, the heights of young women can be modeled by a normal distribution with a mean of 64 inches and a standard deviation of 2.7 inches. What's the probability that we randomly choose a woman and we find that their height is between 60 and 66 inches? So for this example, we are going back to Z-scores and that yellow table that we used to solve all our Z-score problems. We draw out our normal curve. It has a mean of 64 and a standard deviation of 2.7. We want the probability of choosing someone between 60 and 66 inches. So we set those boundaries, we shade that area, and we need a Z-score for each of those red lines there. So our first Z-score for the 60, okay, we subtract the mean and we divide by the standard deviation. So here is our Z-score equation. All right, the Z-score for this value, the 60, is negative 1.48. And then we do the same thing for 66. 66 minus the mean, divide by the standard deviation, z-score 0.74. We then go to that z-score table, that yellow table, and we'd look up each of these numbers. We'd see that negative 1.48 corresponds with 0.0694, and this z-score gives us 0.7704. If we want this area in between those two, we're just going to subtract those two numbers to get our answer. There's about a 70.1% probability that a randomly selected young woman will be between 60 and 66 inches tall.